Good afternoon, everyone. My name is Andrew Purchase, and today I'm presenting our paper, which is a comparative study of fire safety provisions affecting evacuation safety in a metro tunnel. My fellow authors on this were Carl Friedoff and Daniel Roseberg. Just before I get started, I just want to give a little bit of a background on metro tunnels and also some of the typical fire safety strategies employed in metro tunnels. So in very general terms, metro tunnels are quite geometrically simple. You've got a bunch of connecting tubes or boxes that come together at different places and they connect to stations. So when we tend to model them in FDS, we tend to do it quite simply. We don't model the whole network, it's not practical to do, we just model a segment of the tunnel. So whilst it's geometrically simple, aerodynamically it can be quite complex. So the aerodynamics at the start of a fire can vary quite considerably. So other vehicle movements in the tunnel, the incident train, the piston effect associated with that, and any normal ventilation that's happening or atmospheric conditions such as wind can mean that it's quite dynamically complex what the air is doing. So if a fire does occur on a train while it's in a tunnel, the typical strategy is to continue to the next station. It's much easier to manage evacuation there than it is in the tunnel. But of course, this is not always possible. Sometimes it might be the case that congestion prevents the train from getting to the next station, or it could be that a mechanical fault or the fire itself causes the train to be stuck in the tunnel and hence evacuation is required. So whilst it's an unlikely event, it's usually deemed credible enough to provide evacuation provisions in a tunnel. So what are typical rail tunnel evacuation provisions? Well, based on a survey of tunnels from around the world, there seems to be some provisions that are pretty typical. So it's quite common to have walkways that have emergency lighting to assist with evacuation. It's also common to have regular exits once the tunnel gets over a certain length. But that's where it starts to end. That's where it starts to deviate a little bit. So some provisions tend to vary quite a bit. The one that interests me the most is the longitudinal ventilation. I'm originally from Australia and I've worked quite a bit in the UK and the US, and in my experience at least, it's almost a given that the tunnel will have longitudinal smoke control. I moved to Sweden about a year ago and I found that that's not always the case. So I see examples where sometimes it's provided, sometimes it's not. And that was a little bit conflicting for me, given my previous experience. The other thing that tends to vary quite a bit is the walkway width. So for instance, an NFPA 130 compliant design would tend to have a walkway width that was about 0.7 metres. But then there's other examples in Europe where it's around 1.2, and furthermore there's examples where it could be as high as 1.5. The walkway elevation also tends to vary. So some tunnels have a walkway that's at track level, some have them at level with the train floor, and of course it could be also somewhere in between that. The other thing that tends to vary a bit is the exit spacing. So again, an NFPA 130 compliant design would tend to have an exit spacing of around 240 metres, and that would be pretty typical in a place like Australia as well. But then there's a lot of examples when it's greater than that, so it's 300 or it could be 500 or even greater than that. So why is there so much variation in what's provided in a tunnel evacuation design? Well, that's quite simple. Things vary around the world. Standards vary, people's perceptions of safety vary. Also, it could be that a system has certain constraints, so you can't provide this, you can't provide that. Or it could be that you're adding new tunnels to an existing system and it's convenient to maintain a strategy. So if the walkway is a certain configuration, you just keep with that for consistency. I think the problem though is it can be confusing when these provisions are looked at in isolation. So sometimes you'll be working on a project and another design discipline or a stakeholder will come to you and they've seen a tunnel somewhere else in the world and they'll be like, why do we have this provision? Why don't we have this? Blah, 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 blah. And you find yourself in the position where you're having to defend your design. You've got to demonstrate an acceptable level of safety, but also a solution that's cost effective and optimal in terms of its impact on other design disciplines. This is particularly the case for tunnels because things like walkway widths can affect the overall tunnel envelope, which then implicates the cost. So just to give a bit of summary here of what we're trying to achieve and how it could be used. So what we're trying to do is investigate a range of tunnel evacuation design configurations and the impact these have on occupant safety. The focus of this is on metro tunnels, but the concept should be equally applicable to other rail tunnel designs. The way that we did this is we did CFD and evacuation modelling and compared results on the basis of visibility, but also on the FED regarding asphyxiants. As with any analysis, there are certain limitations here. We've used a set bunch of parameters. We've made simplifying assumptions. So, of course, the results here only apply to the work that we've done. It could be that if something varied, like the fire size, results or outcomes could be quite different. So the intent of doing this was to provide a comparative set of results that could be used by the fire safety designer when they're coming to design their tunnel. So it gives people something to think about more than anything. So to do the work, we had to come up with some scenarios to analyse. So in essence, we did 12 CFD simulations and 144 evacuation scenarios. The table here shows a bit of a summary of the parameters that we looked at, and the ones that, it might be a bit hard to see, but the ones that are shown in the highlighting are the ones that were actually selected. So to just touch on a couple of these, for instance, the fire location was selected to be towards the middle of the train, and this was considered reasonable when you're comparing a ventilated and a non-ventilated solution. So if longitudinal ventilation is provided, the typical strategy is you blow it one way depending on where it is in the train. But if it's towards the middle of it, a judgment might need to be made. So this seemed a reasonable location to have it when comparing the two solutions. The fire size and growth rate were pretty much nominally selected, and of course this may not represent the absolute worst case for a metro train in a tunnel, but it's probably something that could be a credible design case. We also looked at different grades, so a flat tunnel and a tunnel with a 4% grade. The grades here are quoted relative to the main occupant movement, so plus 4% is up towards exit 2. Also looked at different velocity conditions, so no velocity at all in the tunnel, a 2 metre per second wind, which was applied as a velocity boundary condition, and critical velocity. So that was a fixed velocity boundary condition that was calculated based on the equations in NFPA 502. In terms of the evacuation scenarios, we looked at a 0.8 metre walkway, a 1.2 metre walkway, and the occupant numbers was around 900. So that was 300 people per car. There was a 3-car consist. We looked at different exit spacings, so 240 metres, 300 metres and 500 metres, and different walkway elevations, so a walkway that's at track level and one that's at the train floor level. So just briefly touch on the CFD modelling. This was undertaken with FTS version 6. The total domain length was 900 metres, which allowed for an 140 metre long train and exits of 500 metre separation or greater. 2 tunnel cross sections were looked at. There was a 22 square metre tunnel, which is this one shown here, and a 28 square metre tunnel, which is here. So both tunnels could accommodate a 1.2 metre walkway, but I think the reality is in this one, getting that in there would be quite difficult practically in a real tunnel due to curvature or tunnel surfaces. But for the purposes of this exercise, it's included in the analysis. Each model had devices for measuring tenability, so visibility, temperature, and so on. So the results for visibility are presented here as space versus time, or XT plots. So these plots show the distance along the fire along the x-axis and the time in minutes along the y-axis. The train is shown as a blockage here, and the exits, or different exit spaces, are shown as vertical lines. The colour bars have been clipped at 10 metres, so anything greater than 10 metres is shown as white, and the colour bar shows the remaining contour levels. So from these results, the ones on the left here are the track level walkway and the elevated walkway. Obviously for the track level walkway, results are slightly better because this is measured at 2 metres above the walkway, so it's lower in the domain and visibility is better along the walkway. The next set of results are comparing visibility along the walkway with different tunnel grades. So the one on the left here is a 0 grade, and the one on the right is a 4% grade. So visibility on the walkway varies quite a bit depending on the grade. So for instance, when the fire's on 4% grade, visibility on the uphill side is lost much sooner, whereas visibility on the downhill side is not too bad. This is because obviously buoyancy is driving the smoke uphill and causing that visibility to be lost sooner. The third set of results are with longitudinal smoke control. So again, the figure on the left here is in still air, so no smoke control applied. And the one on the right here is with a velocity applied on the left-hand side. What's interesting here is how similar this result is to when the fire was on a 4% grade. Visibility is lost a little bit sooner along here, but the overall outcome is very, very similar. And then the final visibility slide I want to show is comparing the different walkway elevation with longitudinal smoke control. So the one on the left here is a track level walkway. The one on the right is an elevated walkway. The results are slightly better for this case than they are for this. And again, that makes sense. People are lower in the tunnel compared to this case. What I think is most interesting about these results is the visibility conditions that occur across the length of the train. So we're applying a velocity here. Then we've got the train, which causes a blockage. So the velocity becomes higher because the area is lower, and that causes a bit of dilution along there. So visibility looks a bit better. It gets to the end of the train, the flow expands, and then visibility is worse relative to across the train. So the results are presented so far are for visibility, which give a good indication of smoke movement in the tunnel and tenability. But they don't really tell us how the different walkway widths affect occupant safety. So to do this, we undertook some evacuation modelling. To do this, we developed a 1D evacuation model for rail tunnels. So the reason for this was it was pretty simple to do. We've just got a straight tunnel, so the evacuation routes are pretty straightforward. And doing it this way gave us complete control over the correlations we used. We could also implement a reduction in walking speed with reduced visibility. It also allowed us to script it very easily. So we had 144 evacuation scenarios, so we could run them with pretty much no human input once the model was set up. So the paper talks about this in more detail, but just to give a quick overview, the flow rate along the walkway was governed by the equation here from Lundström. The flow rate along the walkway with the train, so the flow rate is a little bit less, it's considered like a corridor, and we sought guidance from the Swedish building code for that. The walking speed in smoke is governed by this relationship here by Fridolf. Ultimately, the walking speed along the walkway is a function of how much crowding there is, the flow rates governed by the equations above, the visibility conditions, and also the agent characteristics. So we had 3 different agent characteristics. Some agents had a maximum walking speed of 0.8, some had a maximum walking speed of 1, and some had a maximum walking speed of 1.2. So for the evacuation results, there's 4 slides of this, and I'll just explain briefly what these plots mean. I hope people up the back can see this, but the blue symbols are for 0% grade, the red symbols are for 4% grade. The squares are for still conditions, the circles are for pressure boundaries, so the 2 metre per second wind, and the triangles are for critical velocity. Along the x-axis are the different exit spacings, and these plots are divided in 2. So this side shows a track level walkway, this side shows an elevated walkway. And for each slide, there's 2 sets of results. So there's results for a 800 millimetre walkway in a 22 square metre tunnel, and results for a 1200 millimetre walkway in a 28 square metre tunnel. The results that are shown on this slide are for the maximum FID, and these have been truncated at 1. So any value that's greater than 1 is shown as unity here. So the highest values are seen for a 500 metre exits with an elevated walkway, and the lowest values are seen for a 240 metre exit with a low level walkway. And that makes complete sense. The longer you have to walk and the smaller the walkway and the higher it is, the more likely you're going to be exposed to low visibility, therefore your walking speed is reduced and your total evacuation time is increased. And then there's a fair bit of spread in the results. And this seems to vary quite a bit depending on the grade, the velocity conditions, and the area of the tunnel. So it's quite a complex interaction between all those different parameters. The next slide is the number of people who are exposed to an FID of greater than 0.3. Point 3 was chosen because there's several jurisdictions around the world where that's a typical acceptance criteria for evacuation in a tunnel. These values here have been normalised by 600 because that's the typical number of people that walk towards the furthest exit. So it's convenient to do because it normalises the results between 0 and unity. So the results here are pretty much the same as the last slide. The highest values are seen for the long exit spacing, the lowest values are seen for the shorter exit spacing. So pretty much exactly the same result as the last slide, which is to be expected. This slide shows the low visibility exposures, and this was nominally selected. So a person was counted to be exposed to low visibility if they're in less than 5 meters visibility for greater than 10 minutes. So for this, outcomes aren't as clear with different velocity boundary conditions. So for the shorter exit spacing, it tends to be the case that conditions are worse in still air. However, for conditions where there's some airflow in the tunnel, be that from forced ventilation or due to the effect of grade, conditions tend to be worse for the longer exit spacings. And that seems to be the case that when it's a short exit spacing, relatively speaking, people are exposed to low visibility for longer, whereas it's a longer exit spacing, people tend to start outpacing the worst of the smoke layer when it's still air conditions. Whereas when there's airflow in the tunnel, those people tend to be exposed to that because it's being driven across them. And then the last slide is the total evacuation time. So these is quite obvious. As the exit spacing increases, of course, the total evacuation time increases. People have to walk longer to get out. And then as the walkway width decreases, the evacuation time increases as well. So compare these results to these ones here. Longer evacuation times also tend to occur when the walkway is elevated, and that's because, again, people are higher, they're exposed to low visibility, which is reducing their walking speed, so their total evacuation time is longer. And the other thing that we noticed was that conditions tend to be improved for a larger tunnel. So the result here has two effects. It's a larger tunnel and it's a wider walkway. But in the paper, we look at the same tunnel area with the two different walkways, and the area makes an effect. And that's because, obviously, it's a larger volume, so it tends to be the case that visibility is better compared to the tighter tunnel. So just to sum up, a lot of the results I've shown today, I think, would be pretty obvious to an experienced practitioner. I don't think there's anything too groundbreaking in them. What is, I think, challenging is that sometimes stakeholders and other design disciplines don't appreciate how much of an effect a change can have on the fire safety design. So based on the results I presented, an increased exit spacing and reduced walking width reduces tenability, a decrease in the exit spacing and a wider or lower level walkway increases tenability. And that's pretty obvious. I don't think people need to model to understand that effect. What I think is interesting is the effect that tunnel grade has and how much the area impacts the results. And I think it's important that when we're modelling these things, those things are accurately taken into account. I think it's also important to understand the different outcomes with different velocity conditions. I think it's really important when you're looking at tunnels that you either resolve the velocity boundary conditions well, or you look at a range of conditions that it could be, because what happens at the time of the fire could vary from anything from completely still air to meters per second of airflow. So that lends the question, what is the best configuration? Well, there's no answer to that. It really depends on each, or the specifics of each project. So I'm not standing here today advocating that any solution here is the best solution. It really depends on the project that people are working on. If cost and there was no other constraints there, then obviously short exits and wide walkways would be the best solution, but that's never the case. We always have to do trade-offs to arrive at an optimum solution. And that's really where the value is in modelling like this. We can come up with that solution in a relatively short period of time, I guess. So thank you very much for your attention, and please, if you have any questions.
Did you take into account in the time to get out of the train? Because usually it takes quite a long time just to be able to get out of a very crowded train. And also, I saw that the low-level corridor showed similar evacuation times when I was expecting that just getting out of the train into a 2 meter below corridor would take more time, and it's accident prone as well. So I don't think it would be a safer situation.
Yep, so that was one of the parameters that we kept constant, and we talk about that in the paper. So we wanted to kind of rule out a few variables because there was already a lot of variables to consider. So the evacuation time for the train is kept constant, and those type of considerations, I agree. You need to look at that as well, because the time out of the train and those other things would come into play.
For the CFD part of this, did you do any verification for the mesh you are using, or because FDS is not that great on solving boundary layer, and in tunnels, especially if you apply a wind in one side of the tunnel, boundary layer can play quite massive difference on your results. So have you looked at that in any chance?
No, not any great deal of sensitivities. I mean, the pressure boundary, the pressure we applied doesn't realise the velocity it was based on, of course. And it breaks up as it passes across the train, but we haven't looked at that in any detail.
Because sometimes if you apply a boundary on the inlet boundary condition, in tunnels, for instance, it can develop a parabolic shape, or it can be a turbulence where it is just a profile in across the tunnel. So I'm not pretty sure that FDS is capable to solve that in very accurate way.
So there's some disturbance there to disturb that layer, but yeah, we haven't investigated that. No.
Other questions?
Right. The analysis that you performed was on an electric-driven train coach?
Oh, no, sorry?
The analysis was performed on an electric-driven coach? I mean, in terms of the heat release rate and the extinction coefficient that you chose?
So as I said, those parameters were pretty nominal. So we just selected a value for a fire size. And like I said at the beginning, there's limitations to this. If it was for an actual project, you would go into a lot more detail.
Anybody else? Yeah.
More a comment than a question, I guess. It's just, I guess, echoing what you're saying. We've had a number of projects where you often have to go in to defend your design against other disciplines.
Yep.
And actually being able to pull out modelling to say, well, this is kind of how we think the people are going to evacuate, this is how we think the fire and smoke is going to behave, often makes a very powerful case to sort of defend your corner, if you like.
Yep.
And to get the best from fire engineering. Obviously, it's always that balance of how much of the client's money you're spending.
Exactly.
Okay, great. Well, thank you very much, Andrew.